Good afternoon, students. Welcome to the lecture of real analysis. In the last lecture, we have seen some important deduction related to Riemann-Stieltjes integrations. The first deduction we have seen is integration f d alpha is lambda times alpha b minus alpha a. Integration f d alpha is knowing the function is continuous. This is f zeta minus alpha b alpha beta minus alpha a. And the remaining deductions are also going parallel deductions we have seen already in Riemann integration theory. Let us move ahead towards the today's lecture, in which we are going to prove an important theorem related to refinement of partition. As of in Riemann integration theory, we have seen that the upper sum decreases and lower sum increases with respect to the refinement of partition. Then here also there is the same kind of effect is going to hold. That is, again upper sum decreases, lower sum increases. Therefore, let me write the statement of the theorem. Actually, we have started the theorem in the last lecture, correct? But due to network issue, we couldn't complete it. So let us start from the beginning and we will try to complete the theorem today. Under the refinement of partition, we are going to study this theorem, where the theorem tells that if P star is refinement of capital P, then prove that. What we want to prove? U P star F alpha is less equal by U P F alpha. What this symbol means actually, this is the upper sum with respect to the partition P star of a function F with respect to alpha. Okay. Same thing we will write for lower sum. L P star F alpha is greater equal by L P F alpha. Okay, this is what we want to prove. Now we have to prove the theorem into two different parts, one for upper sum, one for lower sum. In case of considering the refinement of the given partition, to execute the proof of this theorem, what we will do? We will take only 1 point extra in the refinement. Okay, there is only 1 point more than P. Okay, assuming the point, say zeta is extra and which lies in the ith subinterval, we will just prove the corresponding theorem. Okay, therefore let me write what is the partition. Let P equal to x naught, x1, x2 till xn is equal to b. Be a partition of given interval AB. Now what we are going to understand, we are going to suppose here, suppose P star contains just 1 point more than P. Okay, why this is 1 point we were considering? Just in order to make the result to be proved in the simplified manner. Okay, let this extra point be, zeta lies in, where it is going to lie? In ith subinterval, say xi minus 1 to xi, that is xi minus 1 strictly less than zeta, strictly less than xi. Why we are considering strictly less? Because if we consider less equal or less equal as the inequalities, then zeta may coincide with xi minus 1 or it may coincide with xi. But if it is going to coincide with one of the end point of this ith subinterval, then this could not be an extra point as we have considered for the refinement. Therefore, we are considering strictly the point zeta lies between xi minus 1 and xi. Now, next step we will consider is, as the function is given to be Riemann integral. Riemann integral means it is bounded. If it is bounded on the whole interval A, it is to be bounded on each subinterval in the given partition. Therefore, we will just write on the bounds of the function in every subinterval. Therefore, here I will write as f is bounded over the entire interval AB, comma, it is bounded bounded on every subinterval. Every subinterval. Now, as we are proving the first result for upper sum, we will just deal with the suprema values. Therefore, here we will write let W1, W2, and capital EMI be the supremum of F in. Okay, in which intervals? In intervals. Okay, first W1, the suprema I am going to consider in the interval xi minus 1 to zeta, W2 be the suprema in zeta to xi, and mi be the suprema in the ith subinterval xi minus 1 to xi respectively. See, this is what I want to tell you. This is the interval. Suppose this is my ith interval xi minus 1 to xi. Zeta is the point extra considered. Then we are going to define W1 to be the suprema in this interval, suprema of F in this interval, W to be the suprema of F in the interval zeta to xi, and over this interval we are going to consider the suprema to be mi. Now, what is the relation between W1 and mi, W2 and mi? In the last lecture also we have discussed this.
Less equal.
Yes, it is less equal. W1 is less than or equals to mi, W2 is also less than or equals to mi. Now, in order to prove this result, UP star F alpha less than or equals to UP F alpha, what we will do, we will consider the difference UP star F alpha minus UP F alpha, and we will prove that difference is less than or equals to 0. The difference is non-positive. For this, I have to write both the values of upper sums. Okay, what is UP F alpha? Let me write it. M1 delta alpha 1, M2 delta alpha 2, so on. Somewhere here is my ith subinterval, say Mi delta alpha I, and continue. Last one will be Mn delta alpha n. Now, what is UP star F alpha? First term as it is M1 delta alpha 1, second is M2 delta alpha 2. Okay, now the only change is this ith subinterval is being divided into two parts. Therefore, we will write the suprema of the function in every subpart and its length. Therefore, this is W1. What is the length of this interval? Instead of length, actually is at alpha values. No? In Riemann integration, we are writing it. Therefore, what should I write
Alpha
here?
of zeta minus alpha of xi minus 1.
Good. Alpha zeta minus alpha xi minus 1. What about the second one? This W2 into
Alpha xi minus alpha zeta.
yes, alpha xi minus alpha zeta. And the last term, continuing this way, the last term Mn delta alpha n will be as it is. Okay. Now let me call this to be statement number 1 and let this be statement number 2. Now what we will do, we will subtract 1 from 2. Subtracting 1 from 2. So what will be the effect if I subtract? UP star F alpha minus UP F alpha. If you look at both the equations very carefully, all the terms are going to cancel one another. Which term cancel? M1 delta alpha 1 cancels one another. M2 delta alpha 2 cancels one another. Only this term is not going to cancel. Which term? Mi delta alpha I, W1 into this term, W2 into this term. All the rest terms are going to cancel one another. Therefore, we will write only the terms which will left with us. Okay. Therefore, the term left with us will be W1 into this bracket added with W2 into this bracket minus Mi delta alpha I. Correct, no? W1 into alpha zeta minus alpha xi minus 1 plus W2 into alpha xi minus alpha zeta minus Mi delta alpha is there. Delta alpha may I write the first step, let me write delta alpha itself. In the next step, I will write its value. Okay, now what is delta alpha I? Yes.
Alpha I minus alpha I minus 1.
Is it alpha I? Or alpha xi it is?
Alpha xi.
Good. This is alpha xi minus alpha xi minus 1. In the definition of Riemann integration itself, we have written. Let me show you the definition. Riemann integration. Where we have written this? First lecture. Delta alpha is alpha xi minus alpha xi minus. Correct now? We have just substituted the value. Now, next step. This proof goes very parallel to the proof we have completed in Riemann integration. If you remember, you can tell me what is the one term we have adjusted in order to get the required result. One term we have added and subtracted. If anyone remembers, you can tell me. One adjustment we have made. Time being, let me multiply by the terms W1 and W2 in the brackets. Do you remember the proof we have written in Riemann integration UP star F minus LP star minus UP F is less than or equal to 0. One term we have added and subtracted.
Mi zeta?
Yes, it is mi zeta. Correct. Maybe at this step, what should I do? Instead of mi zeta, what should I add and subtract?
Mi alpha zeta.
Good. Mi alpha zeta. Therefore, I have to add and subtract the term mi alpha zeta. Here I have written the terms. Okay. Now here what we are going to do? We are going to add mi alpha zeta minus we are going to subtract. Same thing. And this we are doing just for the sake of adjustment. But here I will write adding and subtracting. Can anyone tell me the next step then?
Alpha zeta common.
Yes, we have taken the coefficients of alpha zeta, alpha xi minus 1. Let us collect the coefficient. The first coefficient we will collect of the term alpha zeta. Alpha zeta. Okay, let me draw another color pen. Here this is one term W1 alpha zeta. Therefore the first coefficient I got is W1. Next is here it is instead of plus mi we are selecting minus mi. Okay, therefore what is the coefficient of alpha zeta? Is it W1 minus mi? Next we will collect the coefficients of alpha xi minus 1. How many terms we have? Alpha xi minus 1, this is one term. Here is another term. What are the coefficients then? Mi minus W1. Correct now? This is mi minus W1. Next, let me collect the coefficient alpha xi. How many terms do we have taking the terms alpha xi? Here is one term. Here is another term. Therefore, if I take alpha xi common, what are the terms left with me?
W2 minus mi.
Good. This is W2 minus mi. Now, which more term is left with us? One more alpha zeta left. Correct now? Here, let me find out the coefficient of this alpha zeta. Only two terms are left now. Then if I collect alpha zeta common, what will be the coefficient?
Mi minus W2.
Good. This is mi minus W2. Okay. Now looking at this structure, now again we will collect the terms of W1 minus mi and W2 minus mi. Now you tell me the coefficients of W1 minus mi. This is the first term W1 minus mi. This is the second term. If I collect W1 minus mi common, here I have to adjust one negative. Correct no? Then for what is the coefficient left with us?
Alpha zeta minus alpha xi minus 1.
Good. Alpha zeta minus alpha xi minus 1. And if I collect similarly W2 minus mi, this is hmm, if alpha xi, if I take the coefficient W2 minus m, hmm,
Alpha xi
alpha
minus
x,
alpha zeta.
good, alpha xi minus alpha zeta. Okay, and let me call this to be my third equation. What is the left hand side? Don't forget, u p star f alpha minus u p f alpha. Correct now? Now look at the every term involved in this product. This is the addition of two products, no? The addition of two products. What about this value w1 minus mi? What is the relation between w1 and mi we have written? W1 is
Less equal.
less equal by mi. Then what is the value W1 minus mi? Less equal 0 or greater equal 0?
Less equal 0.
This is less equal 0. What about this? W2 minus mi? Same,
Less
na?
equal 0.
Less equal 0. Now we have to think of this bracketed terms. What is the hint known to us? Alpha is monotonically increasing sequence. Alpha is monotonically increasing sequence. Therefore, what would be this nature? Alpha zeta
Greater
minus
than
alpha
0.
x7. Yes, it is greater than 0. Correct, na?
Yes, ma'am.
Yes, it is greater than 0. If it is greater than 0, non-negative into means a negative term into positive. Negative into positive. Negative into positive, multiplication will be negative or rather
Negative.
non-negative I will call. And this product is also giving us non-negative. What is the addition of two non-negatives?
Again non-negative.
Non-negative. And if this difference is non-negative, hence the proof holds now. This term is less than or equals to 0, means UP star F alpha is less than or equals to UP F alpha. Okay. Now we will just write the reasons. Means W1 is less than or equals to Mi. It implies W1 minus Mi less than or equals to 0. W2 less than or equals to Mi implies W2 minus Mi less than or equals to 0. Also, alpha is monotonically increasing function. Monotonically increasing function. Therefore, if I have xi minus 1 strictly less than zeta strictly less than xi, what about the corresponding values? Xi minus 1 strictly less than alpha zeta strictly less than alpha xi. Therefore, what this term gives us, which implies, what about the value alpha zeta minus alpha xi minus 1 greater than 0, no? This if I shift to the right alpha xi minus 1, then this will be greater than 0. Similarly, what about alpha xi minus alpha zeta?
Greater
It's
than 0.
also greater than 0. Therefore, here I will just write equation number 3 becomes. Thus, equation 3 becomes. What it is going to become? UP star F alpha minus UP F alpha less than or equals to 0, which implies UP star F alpha is less than or equals to UP F alpha. Correct now? Therefore, the proof, if you observe, this is going to be very similar to the proof we have studied in Riemann integration theory. Okay? Now let us write the proof of the second part. Or whether you want to do the second proof, you want to try for the second one? Proof goes on the parallel lines as of in the Riemann integration. You tell me, should I take the proof or you want to try for the proof?
We will try, ma'am.
Sure?
Try, ma'am.
Yes, ma'am.
Yes, ma'am.
Because the proof goes similar to the Riemann integration. Okay? So let me just leave the 2 pages in between to prove that L star F alpha. Now we want to prove it is greater equal by LP of alpha. Here what we have forgot to write, if P star contains one point only, then the result holds. Therefore, if P star contains more than P points or more points, then the same result will hold. This statement you have to mention. Okay. Let me just leave the two pages in between and let me go for one more theorem called as condition of integrability. All the rest theorems are going to follow as it is in the Riemann integration. But we are going to just repeat the proof of all the theorems. What is the condition of integrability we have seen in Riemann integration? Yes. What is the condition of integrability in Riemann integration? Hello students, am I audible?
Upper and lower integral must be equal.
Okay, that is the definition, Arbox. What is the condition? UPF minus LPF is
Less than epsilon.
The same we are going to prove. Integrable with respect to alpha on closed interval AB if and only if for every epsilon. Now here Arbox theorem is also going to exist as it is. So we were not writing the statements of all in between theorems. Okay, I am taking the proof of directly condition of integrability. For every epsilon greater than 0, there exists a partition P of closed interval AB such that UP of alpha minus LP of alpha less than epsilon. As it is the condition of integrability and it was taken in with an only theorem, we have to prove the result in two parts. First, we will prove the necessary part of the result. In the necessary part, what will be my assumption and what to prove? Should I assume the condition and prove integrability?
F is integrable and proving UP of alpha minus LP of alpha is less than.
Good. For here, let me assume that F is integrable, correct? With respect to alpha. And what to prove? UP of alpha minus LP of alpha less than epsilon. This is what we want to prove. Do you remember how the proof we have given in Riemann integration theory of condition of integrability? I think you have started your study because in the next month you are going to face the exams, university exams, right? To prove
Lower integration equal to upper integral of function.
that is integrability condition, definition. How we have given the proof is my question actually. The proof we have given by using the Arbox theorem, if you remember.
Yes, ma'am.
How we have written the Arbox theorem? We have taken two different partitions, P1 and P2. We have written the statement of the Arbox theorem once for upper sum, once for lower sum, taking P1 and P2 are the two partitions. Later, we have taken the common refinement of both the partitions, P1 and P2. And just now we have seen that upper sum decreases with respect to refinement. And using this part, we have proved UPF minus LPF is less than epsilon. Let me show you how. Okay. Let epsilon greater than 0 be given number, because everything we are proving by depending on epsilon itself. For epsilon greater than 0 be my assumption. Now we what the fact we know, upper integral and lower integral are infimum and supremum of the upper and lower sum. Knowing this fact, we have found the partitions P1 and P2. Since the upper and lower integral maximum and supremum of upper and lower sums respectively, there exists a partition P1, P2 such that, how such that we have written U P1 F alpha strictly less by upper integral plus epsilon. Okay, and for the sake of adjustment, we were doing it as epsilon by 2 later. But as the function is assumed to be integral, therefore this upper integral is nothing but the actual integration. Secondly, for another partition P2, we have written LP2F alpha is a greater by lower integral minus epsilon, where again lower integral we have replaced by actual integration. Right? Let me call it as statement 1 and statement 2. Now for whatever the two partitions we have taken, we are taking their common refinement. Therefore let P is equal to P1 union P2 be the common refinement. Be the common refinement. What is the relation between the upper sum and its refinement? That is any arbitrary partition, say this is a refinement and this is what we have a partition. What should be a relation between the two sums? Knowing P is partition, just now we have proved that this upper sum decreases. Correct, no?
Yes, ma'am.
So what UP1 of alpha we have written just now? This is strictly less by integration a to b f d alpha plus epsilon from 1. From 1 we have written this part. But what for this integration? What for this integration? From 2, may I say the integration value is less than by lower sum plus epsilon?
Yes, ma'am.
Therefore, may I write this is L P2 F alpha plus epsilon plus epsilon. How? This is from 2. Okay? Or you can write it how it is from 2. How it is from 2? L P2 F alpha strictly less by integration a to b f d alpha minus epsilon we have. Therefore, integration a to b f d alpha it's greater now. Wrong inequality I have mentioned. So this is less than by L P2 F alpha plus epsilon. Correct? But we want to prove actually this is epsilon. So what should be y adjustment correspondingly? Epsilon by 2?
Epsilon by 2.
Here it is epsilon by 2, here it is epsilon. In this statement also I have epsilon by 2. Correct? Now what is the relation between the lower sum with respect to P2 and lower sum with respect to its refinement? L, P, F alpha na? Epsilon by 2 is plus epsilon. Already it is strictly less. This term is less than or equals to LPF alpha. Correct or not?
Yes,
Which
ma'am.
relation I have used? L P star F alpha is greater
Than equal.
L P F. This relation I have used. Okay. Now next step, what should I write? We shift this lower sum on the right, left. Because UPF alpha minus LPF alpha is less than epsilon. Hence the proof of the condition of integrability. In the proof of condition of integrability. Now we will go for part 2, sufficient part. Now we want to reverse our assumption. What will be my assumption now? Let us assume UPF alpha minus LP of alpha is less than epsilon. Okay, and what to prove? The function is function f is integrable with respect to alpha. Proving integrable with respect to alpha means you will just prove upper integral is equal to lower integral. Okay. Now here what we will use, we are going to use a relation which we have written in the definition itself. For any partition P, we know that what we know LP of alpha. You have to tell me the relation, okay? Lower integral, upper integral, UP of alpha.
Less equal, ma'am.
Less equal.
Actually, whatever I have written a type, knowing the type, you are telling me the answer less equal or not. असं मी लिहिलंच आहे ना सरळ ते लेस इक्वल असं काही म्हणताय का खरंच माहिती आहे आपल्याला
No, ma'am. खरंच म्हणते.
टेल मी द रिझन वाय लेस इक्वल हिअर
Because lower integral is supremum of lower sums.
Good. So this is supremum and relation between with arbitrary lower sum is greater equal. Lower integral is always less equal by upper and the same upper integral, this upper integral is infima of set of upper sum. Therefore this is my infima value. Correct, na? Okay. Now looking at this term, what we are going to do, we will divide the inequality into two parts. How I am going to divide it? See, it is ELP of alpha less than or equals to lower integral. First part. Now I will take the second part as upper integral of d alpha is less than or equals to u p of alpha. Next step, what we will do? Adding both the inequalities. What we will get if I add both these inequalities? Upper integral plus lower sum less than or equals to lower integral plus upper sum. Now what we will do? We will take integrals on one side, sums on one side. To the right we will get UP of alpha minus LP of alpha. But what we have assumed, this term is less than by epsilon. This term is less than by epsilon. So we got upper integral minus lower integral is less than by epsilon, where epsilon is any positive number. But what is the quantity on the left? As of this relation holds, lower integral is less equal by upper integral. What about this value? May I say this value is non-negative or non-positive?
Non-negative.
Non-negative. A non-negative term which is less than every positive. What is the possibility?
0.
0.
The 0, right? Here I will write since LHS is non-negative. LHS is non-negative. Epsilon is arbitrary positive number. Arbitrary positive number. The above inequality holds only if when it is going to hold only if this is 0. If it is equal to 0, what we can say? Upper integral difference is equal to 0. Na? Therefore, may I write this is equal. And if these two are equal, the function is integrable with respect to alpha. Any doubt?
No, ma'am.
This proof of all the theorems. If for your exam there may be a possibility to ask a Arbox theorem also for Riemann-Stieltjes integration. What the corresponding changes you can do? as I have shown in this condition of integrability in the previous theorem as well. Correct? You can do the corresponding changes. Now we will deal with the last section, solving the example. Before the example, we will just see a statement of an important theorem where the theorem will help us to prove the example, to solve the examples. Here the theorem states that if alpha increases monotonically, alpha dash is Riemann integrable. See what I am saying? Alpha dash Riemann integrable, comma, here is bounded and Riemann integrable. Then what? Integration a to b f of x into d alpha. Okay, correct? Now, this is what we want to evaluate. Integration of f with respect to another function alpha. Theorem says that this value is integration a to b f of x into, we will just evaluate d alpha x, and what we know d alpha x is alpha dash of x into d of x. Alpha dash of x into d of x. Therefore, if both the functions are integrable, this is R integrable, alpha dash is R integrable, then what about their product? Will it be R integrable? Yes,
Yes, ma'am.
already, no?
Integrable.
Therefore, this will be Riemann integrable. The product of this, that is integrand, is Riemann integrable, and the integration is taken with respect to x. And if it is taken with respect to x, can you solve the example by using two methods? One of the two methods, by using the Arbox sum or by using the Riemann sum. Correct? No? So this theorem will
Yes,
help
ma'am.
us to solve the example. Therefore, suppose an example is given to you, integration 0 to 1 x dx squared, x dx squared, and if it is asked to solve this by Riemann-Stieltjes integration, by Riemann-Stieltjes integration, then we are going to use this theorem. What is alpha x here? X square, no? What is f? X itself. Therefore, how should I write this? By using the theorem, what is the value of this integration? Is it 0 to 1 x as it is, and integration of dx square? What is the integration
2x.
of dx square? 2x dx. Correct, no? Therefore, what is my new integrand? Is it 2x square? Is it 2x square? The new integrand is. If it is
Yes, ma'am.
2x square, one can solve very easily by using Riemann sum method or any Arbox sum method as well. But there is no as such separate method for solving a Riemann-Stieltjes integration for our syllabus. Okay. So we were solving Riemann-Stieltjes integration example by using the previous methods of Riemann sum or Darbox sums. Okay. In the Darbox sum method, one has to calculate upper sum, then lower sum, then go for finding their upper integral, lower integral, check whether both the integrals are equal or not. If they are equal, the function is integrable, otherwise not. If you prefer Riemann sum method, what you have to do? You have to write SPF, correct? And just keep the limit n tends to infinity. Whatever is the value, if the value exists, function will be integrable. If the limiting value doesn't exist, the function is not integrable. This is very simple as such. Okay. Now here our chapter Riemann-Stieltjes integration completes. Riemann-Stieltjes integration. Or you can solve this one or two examples. Let me show one more example. Integration 2 to 3 3x plus 1 into d of x cube. Say, what will the value then? This is 3x square dx. Let me write the integrand first. Original problem, let me write. then 2 to 3, 3x plus 1 into 3x square dx. Therefore, what is my new integrand? 2 to 3. If I multiply by 3x square, this is 9x cube plus 3x square and dx. This is our new integrand, and just go by solving the Riemann sum or Darbox sum method. Okay. Any doubt with solving the examples also? We have taken many examples of Riemann integration by using the Arbox sum and Riemann sum method. Therefore, I don't want to repeat all those examples. The examples of Riemann Stieltjes integration is actually solved by converting it to Riemann. Riemann integration. Any doubt up to this?
No, ma'am.
Here your second unit of Riemann Stieltjes integration completes. Now we will move towards the third topic of multivariable differential calculus. Now, as this name suggests, multivariable differential calculus, we are going to understand the differential calculus of many variable function. To understand this topic number 3 and topic number 4, we are now going to change our recommended book from Similic Savita Arora to Mathematical Analysis by T.M. Apostol. We are going to change it to T.M. Apostol. If I want to deal with the first definitions of multivariable differential calculus, first you should tell me what is the geometrical interpretation of ordinary differential equation, partial differential equation, so that we can understand why the next derivative type is being defined. Can anyone from the students know what is the geometrical interpretation of ordinary differential equation? Derivative of function of one variable. What the geometrical interpretation is? What for partial derivatives as well? I hope I am clearly audible to the students.
Yes, ma'am.
Do you know this or not? Because unless you know the geometrical interpretation of both the derivatives, actually in the third unit we are going to define a new kind of derivative called as directional derivative. Therefore, one should know why there is a need to define a new derivative called as a directional derivative. Before knowing this, you should know what are the drawbacks or lacunas in the previous theory of ordinary differential equation and partial derivatives. For this, I think you are familiar with the geometrical interpretation of ordinary derivative. If you find ordinary derivative of a function at a given point, it is going to give us the rate of change of the given function or slope of the tangent as well. Slope of the tangent, no?
Yes, ma'am.
What for rate of change also? Two different words we were using, rate of change. You have to explain me both, how it is rate of change and how it is the slope of the tangent. Okay. And in partial derivatives, we were finding the derivative. Suppose we are having a function of two variables f of x, y, z. Then finding a partial derivative with respect to x, what we were doing actually? What is the process we were following for finding the partial derivative? With respect to x, I want the derivative. Have you forgotten all the derivative theory? Let me remind you. I think for finding the partial derivative with respect to x, you are keeping y constant, no? Same thing for finding the derivative with respect to y, we were keeping x constant.
Yes, ma'am. Geometric interpretation माहित नाही मॅम फक्त.
काय माहिती? You must know the geometrical interpretation. Why we are keeping y equal to constant? By keeping y equals to constant, what happens exactly? What is the geometrical interpretation? How can I find the derivative? Because we were going to extend it to a new concept of directional derivative. We will discuss it in the next lecture. Thank you for being with me.